Hi. So last time we stated Gauss's lemma and showed how it could be combined with Eisenstein's criterion to show irreducibility of polynomials in Qx. So we stated Gauss's lemma and showed how Gauss's lemma plus Eisenstein's criterion could give us a criterion for irreducibility of polynomials in Qx. And we also use this to give some applications to field theory. So we showed how to use this for applications to field theory. But we didn't actually prove Gauss's lemma. Okay, so the first task in today's lecture is to actually prove Gauss's lemma. So theorem Gauss's lemma. Gauss's lemma tells us that any polynomial which is non-constant over the integers, which happens to be irreducible over the integers, is in fact still irreducible over the rationals. So take some polynomial with integer coefficients, which is non-constant, and assume it's irreducible. So let f be an irreducible polynomial with integer coefficients of degree at least 1. Then this polynomial is still irreducible over the rationals. Okay, so note that this is not trivial. This is not an obvious statement. It's possible a priori that you could factor the polynomial over the rationals. So you could factor the polynomial as a product of polynomials with rational coefficients. It could be possible that you could do that even though you can't factor it as polynomials, as a product of polynomials with integral coefficients. So this is a non-trivial theorem of Gauss. Okay, this is not, if this looks to you like this is totally trivial tautological statement, then you're not understanding it. There is something real that has to be proved in this lemma, okay? It could be a priori the case that you could factor a polynomial, an integral polynomial, as some product of polynomials with rational coefficients, even though the polynomial can't be factored as a product of polynomials with integral coefficients. There is really something that has to be proved here. Okay, so before we prove this, we need a definition and a lemma. Okay, definition. A polynomial is primitive if the greatest common divisor of its coefficients is 1. So a polynomial fx with integral coefficients is called primitive if there is no common divisor for the coefficients. So if the greatest common divisor of the coefficients is 1. Okay, so just some examples to see the definition. So 7x cubed plus 14x plus 2 is primitive. Well, 2 is prime, so that's just because the leading coefficient 7 is odd. And 9x4 plus 6x is not primitive because the GCD is 3. Okay, so the crucial lemma that will be the key ingredient to prove Gauss's lemma is that a product of primitive polynomials is primitive. So take two primitive polynomials. Then the product is primitive. And proof. So suppose that f and g are primitive, but that the product was not primitive. Okay, so if the product is not primitive, then there exists some common divisor. So then there exists some positive integer c at least 2 dividing all coefficients of the product. Okay, but then we could take some prime factor of c, and the prime factor would divide all the coefficients. So then, if p is a prime factor of c, p divides all coefficients of the product. And now we can use a trick that we've already used in the proof of Eisenstein's criterion, and we can reduce modulo p. So let Q from Zx to Z mod Px be the quotient homomorphism and for any polynomial in H in Zx, let's write H bar x for the reduction. So let's write H bar x for the reduction mod P, i.e. let's define H bar x as Q of Hx, just to make the notation a little bit nicer. Okay, so concretely, if H has coefficients a naught up to an, so these coefficients are integral, then H bar x just is the polynomial we get in Zp by reducing all of these integers mod p, where hi bar is in Z modulo p for all I from 1 to n. Okay, so now what do we have? Well, we know that p divides all the coefficients of fx gx, so then if the product reduced mod p will be 0 because all the coefficients will go to 0. Okay, so we have fx gx, all the coefficients are divisible by p, so this is 0. And reduction mod p is given by the quotient homomorphism Q, so in particular it's a homomorphism. So f bar x, g bar x equals 0. Further, p is prime, so we know from what we proved last time that if we take the quotient by a prime ideal, we get a integral domain. Hence, Z mod P x is an integral domain. So now we have f bar g bar equals 0 in some integral domain. This tells us either f bar or g bar is 0. But in the first case, saying f bar equals 0, well, that's the same as saying that p divides all the coefficients of f. And the second case is the same as saying p divides all the coefficients of g. But if p divides all the coefficients, then the GCD of the coefficients is not 1, so the polynomial can't be primitive. So, i.e., either p divides all coefficients of f, and hence f is non-primitive, or the same is true for g, and either way that's a contradiction because by assumption both f and g are primitive. So either f is non-primitive or likewise g is non-primitive, which is a contradiction. So if f and g are primitive, we've shown that the product is primitive. Okay. Okay, so we can now prove Gauss's lemma, which is telling us that an irreducible polynomial over the integers is still irreducible over the rationals. Okay, so let f be an irreducible polynomial over the integers and non-constant. Okay, the first statement is that we can always write f as the product of a constant by a primitive polynomial. So namely, divide out by the GCD of the coefficients of f, so if we divide by the GCD of the coefficients of f, then we have that f of x, dividing out by the highest common divisor, we can write fx as the GCD times something primitive. So you can always factor your polynomial as a product of some integer times something primitive. Okay, so I would like to prove that f is irreducible over q, but since the constant c is a unit over q, it's enough to prove that the primitive part f tilde is irreducible. So since c is a unit when thought of as a rational element, so it's a unit in Q, because any non-zero integer is a unit in the rationals, because we can divide by c in the rationals, then fx is reducible in Q x if and only if reducibility, you see, doesn't depend on something is some element in a ring is reducible if and only if the same is true for any element differing by a unit. So fx is reducible in qx if and only if f tilde x is reducible in qx. So it's enough to show that f tilde x is irreducible. Okay, so we would like to prove, since we're assuming f is irreducible, we now say it's enough to prove, we'd like to prove that f is irreducible over q, and it's enough to prove that f tilde is irreducible over q. So suppose that f tilde x in qx is reducible, i.e. f tilde is some product of polynomials g and h with rational coefficients. So f tilde is a product of g and h for g, h rational non-units. And since they're non-units over qx, they can't be constants because all non-zero constants over qx are going to be units. So hence of positive degree. Okay, so the first thing to do is to note that we can write g and h as a product of some rational number times polynomials with integral coefficients by just taking out the least common denominator. So if L is the least common denominator, of the rational coefficients of gx, then gx equals 1 over L g hat x. So just by taking out the least common denominator, I can write gx as 1 over L times some polynomial g hat x, where g hat x now has coefficients which are integral because all the coefficients were rational in gx, but I just take out the least common denominator. So once I've cleared out the denominator, I've got something which just has integral coefficients. So g hat x. I can write it as a product of 1 over L times g hat x, where g hat is integral coefficients, just by taking out the common denominator. Okay, but now once I've got some integral polynomial, I can take out the GCD and then get something primitive. So as above, we can then take out the GCD of the coefficients of g hat x to get something primitive. And so I can write g hat x as an integer times something primitive, and then I can put that back into gx to get gx equals m over L g tilde x, where m, L are integers, and g tilde x is primitive. And I can do the same thing for h. So likewise, the rational polynomial hx is some rational number times a primitive polynomial. Okay, so now let's go back to our original equation. We had f tilde x equals gx hx. And both g and h were some rational number times something primitive. So this equals lambda g tilde x h tilde x, where lambda is some rational number. And let's say lambda equals a over b. For integers a and b, and let's take b positive. So also, right, I can always put a fraction in reduced form, so I can assume that the numerator and denominator have no common divisors. So GCD of A and B equals 1. Alright, so I now have f tilde x equals A over B, G tilde x, H tilde x, where all my polynomials are primitive, and the GCD of A and B is 1, or B fx equals A, G tilde x, H tilde x. Okay, so first of all, on the left-hand side, I have B times a primitive polynomial. So, since f tilde is primitive, the GCD of the coefficients of the polynomial on the left-hand side is equal to B. And now if G and H are primitive, then we prove that this means a product is primitive. So since GH, the product, is primitive, meaning the GCD of the coefficients of the product is 1, then after I multiply by A, the GCD of the coefficients on the right hand side is 1. Okay, but so this gives us that A equals plus or minus B, because so the GCD on the left is A, the GCD on the right, so which one did I assume was positive? I assumed that B was positive, so the GCD on coefficients on the right hand side is plus or minus A. So if I want the GCD to be positive, then if A is positive, it's A. If A is negative, it's minus A. But either way, it's plus or minus A. Okay, but then equating the two would give me that A is plus or minus B, but I assume that the GCD is 1. Right, so it's only possible if A and B are 1, or if, well, in any case, right, so this means that A and B are 1. Okay, so either by saying that the GCD is 1, therefore, right, so A equals plus or minus B, but the GCD is 1. So A and B are both the same and plus or minus 1. So AB are plus or minus 1. And then I have the equation fx equals plus or minus gx hx. And then f tilde was reducible, which contradicts the assumption. So these are both integral polynomials. And this contradicts the fact that f and hence f tilde were irreducible over zx. So that completes the proof of Gauss's lemma. So if some polynomial, which is non-constant, is irreducible over the integers, it's also irreducible over the rationals. Okay. So before finishing, I'd like to give one other useful, very simple criterion for deciding when a polynomial is irreducible. Okay, proposition. Let R be an integral domain and take some monic polynomial which is non-constant. So let R be an integral domain. And let fx be a monic polynomial of degree at least 1 then suppose that after reducing mod I for I some ideal, I get something irreducible, then the original polynomial must also be irreducible. So let I be an ideal such that the reduction f bar of f modulo I, in other words, the image f bar x of fx in R mod I x, and assume that f bar is irreducible, then the original polynomial was irreducible. Okay, proof. Suppose f is reducible. Which means I can write f as a product of two non-units. Well then, f bar x equals g bar x, h bar x. So then f bar x is a product of g bar and h bar, so f bar would be reducible, which is a contradiction. So if f bar is not reducible, then f cannot be reducible. Okay, and just note that this argument makes sense because since f is monic, so note that since f is monic, then while the leading coefficient of f is a product of the leading coefficients of g and h, but f is monic, so the leading coefficient is 1. So since f is monic, the leading coefficients of g and h are units. But g and h are themselves non-units. So since the leading coefficients are units, neither of them can be constant. Because if one of them were constant, then the leading coefficient would be a constant. But then if the leading coefficient was a unit and they were constant, then they would themselves have to be a unit, but they're by assumption non-units. So since f is monic, the leading coefficients of g and h are units, and hence g and h have degree at least 1. But since g and h are polynomials of degree at least 1 with leading coefficients non-units, this implies, so we're sorry, with leading coefficients units, then when I reduce mod p, I've still got units. So I've still got, so this implies that the degree g bar x is at least 1. Degree of h bar x is at least 1. So I realize here that I want to have that if the leading coefficients are units, then I would like to say that when I reduce, the reduction of these units is still a unit. That's the same as saying I would like to have that when I reduce, that the ideal I does not contain a unit, or the ideal I is not everything. So let's just go and make the small assumption here that I is not equal to R. So let's say I is a strict subset of R, just to rule out that I'm looking at. So if R is equal to I, then anyway this ring would be 0, which would be totally not interesting. Okay, so then so I've got the degree of G and H, since the leading coefficients are units, the degree of G bar and the degree of H bar is the same as the degree of G and H, which is at least 1. So in particular, G bar and H bar are non-units. Are indeed non-units. So for this argument to work, I need G bar and H bar to be non-units, but that's indeed the case. Okay. So if f could be written as a product of polynomials, then the same would be true for f bar, and hence if f is monic, this implies that f being irreducible mod an ideal I implies that f was already irreducible. Okay, so this is typically applied once again in the case where the ring R is Z. So let me just make the comment that we typically apply the above lemma to R equals Z, and then it says that that if fx is some integral polynomial, and f bar x is sorry, I want it to be monic, with f bar x and z mod p, or in fact more generally z modulo n for any integer n, irreducible, then f is irreducible. Okay, so that's it for today, but in the homework for next week, I'm going to give you lots of examples of applying these irreducibility criteria. Okay, so thanks for listening.